Good morning. So this is number 6 in the series. I was telling Debbie just a few minutes ago, this is a little like those, that end of the school year, maybe the last week or the last day before summer holidays, and there's some fun stuff, and you branch out, and that's what this session is really all about. Yes, there's some physics. The physics is up-to-date physics, as up-to-date as this year's Nobel Prize. And so we'll talk about that, but there are a whole lot of other questions. This series was never about just a period in physics between 1900 and 1930. At least it wasn't in my mind, because there was a period beforehand, there's a period after, and there's a period beyond us to think about. So that's where we're going today. By the way, that piece that you're looking at, that's a cat on a hill in Peru that apparently dates back to 200 BC. Looks like a rather barren hill. So we'll just move along. So let's see. Somebody deliberately muted me. So I'm, all right, well, I've been muted before in my life, but I'm apparently not muted now. Anyway, you can all hear me. So, so that's what this week's, it's still stuck. Oh, wait a minute. Oh, here we are. So every week I've had some hominin at the start, and this is the common ancestor, apparently one of several common ancestors. And for all hominins, the chimps and bonobos, gorillas, orangutans, and us. And it gives me an opportunity to bring up one book here. It's a beautiful one. It's John Gurche works for the constructing what these from various fossils and that kind of thing, what various species might have looked like. And it's a wonderful book. He's a very imaginative writer. And so the pictures you see today are his reconstructions based on very partial fossil evidence. So there's the book, Shaping Humanity, How Science, Art, and Imagination Help Us Understand Our Origins. It really is a great resource. So here we've talked about, in the very first session, we talked about what did our understanding of the universe look like in 1900. And the series ended in 1930, and we talked about all those huge advances in the 3 decades. But we're living in 2020, about to become 21. And I'm going to be asking you to imagine the future writ long. So what's in store for the planet, our sun, and the universe? It's interesting that Penrose got the Nobel Prize this year. He's a theoretical physicist now at Oxford, who did his work in the 1960s. And it was theoretical work on black holes. And it's a very interesting concept because if you think about these huge, huge black holes, enormous ones, by the mergers of many black holes become the vacuum cleaner of the universe. They really pick up all the matter and energy within their reach and kind of recycle it. And in the end, when they kind of end their life, they leak energy and maybe some elementary particles, but that's about it. So we're right back to the building blocks of the universe. So it's an interesting end to the universe. It's also a way of the laws of thermodynamics, the conservation of energy. So black holes really restore the balance in a sense. By the way, that's not in Penrose's writing. So something to think about, what's in store for humanity, our species in the short term. What's short term? Short term in my thinking is not 50 years or 100 years. It's not my lifetime, your lifetime. It's several hundred years, thousands of years, tens of thousands of years, hundreds of thousands of years, even millions of years. And that's the way we have to think about things, I think. Because on that scale, I think the changes should shape, will shape our perspective about life in general now. So what about the future of the Earth, the sun, and the universe? Now, this is an interesting thing. Physics is quite different than the other disciplines in science. It has a lot of theoretical physicists who love to play with math and to speculate what the universe might look like. Now, they're not creating this from nothing. They're creating it on a foundation of evidence, but they go well beyond it. And one of those laws I just referred to is the second law of thermodynamics, which really sets the clock running on the life of the universe, because what it says is that energy becomes less and less accessible as time goes by. It's not lost, but it becomes less accessible, less useful. If you think about the light that's emitted by any star, only a tiny little bit of that, of the quanta of light, ends up on Earth, shining on Earth. Most of it kind of spills out into the universe wide and becomes dispersed and therefore useless. That's what we mean by entropy, energy becoming useless, less accessible. And by that reasoning, there is a clock for the universe. It's probably many, many billions, if not a few trillion years from now, but there is. The sun, our sun is a middling-sized star. It's not large enough I mean, it won't die from in a supernova, but as it burns off hydrogen, Earth, or at least the sun, its mass slowly goes down. And with the reduction in mass, so does its gravitational pull. And therefore, the radiation it sends out extends out into the innermost planets. And that will almost certainly include Earth and maybe even Mars. And if it reaches us, for sure, it'll cook everything on Earth. Now, that's slated to happen in probably 6, 7, 8 billion years, so we needn't worry about that. How do we know that? Because of watching other star systems and what happened to various other stars at various times, and then patching it together. So that's our future as far as the sun goes. The Milky Way I won't say much about, but the universe I will. From the very first session here, the first and second sessions, we learned that the universe was expanding. I mean, that's one of the most crucial things that the first session showed. And well, the question is, and that, by the way, that expansion is accelerating. Now think about the implications of that. If stars and star systems are moving away from one another, then the view from Earth at some point, in any other perspective in the universe, becomes increasingly lonely, doesn't it? And what looks like a very busy sky with lots of stars out there becomes diminished. And eventually, if you follow this logic out to its end, it's a dark sky. And if they move out far enough, it just takes too long for the light to reach us, even at the speed of light. So that's the scenario if the universe continues to expand. But our theoretical physicists have been hard at work. And one of the concepts is, well, eventually it just won't continue to accelerate. Eventually, at some point, it will decelerate and begin to shrink and then collapse in on itself and back to something that looked like or might look like the original singularity that characterized the beginning of our universe. And then if you add on some thought, well, gee, if you get back to the original singularity and there's another possibility of the birth of the universe, well, that's the big bounce. And then there's this possibility of mirror universes, meaning if there is a singularity, perhaps there's another version of our universe on the other side of that original singularity, run by the same natural laws, but antimatter versus our universe with matter. And the clock runs in reverse. It's all very freaky, I know, but it's an interesting speculation of theoretical physicists. Now, Penrose, our Nobel Prize winner this year, as I alluded to earlier, speculates that what happens is, if enough of these black holes merge, and to the point where one becomes really gargantuan enough, then there's the possibility that that black hole will suck in all of the energy and all of the matter into itself, into this singularity, and then leak and restore the universe to some particles and maybe energy. That was Stephen Hawking's idea, anyway. And so you can see the setup for a recycling. So the universe recycles itself at intervals. It's an interesting idea, Penrose. I don't know how you would ever prove it with the evidence that we have at hand, but you know, he's a bright guy. By the way, it was one of the interesting personal bits about him is that I mean, he and his siblings and parents were very bright. And one of the things that they used to walk a lot, and they would play chess in their heads. And that's an interesting thing, to be able to keep in your head where every piece is of the chessboard as an exercise in memory and beyond. So this brings us to, how do scientists work? Well, I think I've introduced you to people who do most of their creative work as a solitary person. And I said that was true of Einstein. It's true of Penrose, our Nobelist this year. In fact, he relates this interesting story. He was wrestling with, well, what happens with black holes? I mean, how does it kind of collect all of this star matter and other matter and energy and pull it into itself? And he couldn't figure it out. And so he was walking with a friend, and it was a busy conversation. They'd been talking for several hours, and it came to, there was traffic on the street, and the conversation stopped. And then he had this aha moment, just like Watson did in the pub. And the sense, gee, I wonder if the shape of the black hole is such that it reflects all energy and all matter toward the singularity. That's rather complex math, but it's a very interesting concept. It wasn't welcomed in the first year after he presented the material, but increasingly it was. And it certainly is Main Street now with the Nobel Prize. Now, how has physics and other sciences, how have they changed in the interim? Well, listen, in that 30-year period that we talked about from 1900 to 1930, this is all low budget stuff. I mean, Rutherford made his own equipment. It actually looks like it in the photographs. None of them had any grants, so they weren't wasting their time on that kind of stuff. And if you look at the Nobel Prizes in the last, well, the 3 years that we've been doing it, one consistent theme is that the big projects have become bigger. They often run for 2 or 3 decades, just as with the black hole project, the black hole at the center of our galaxy. It's 2 large groups working in Chile and Hawaii, and outside of that, hundreds of physicists and mathematicians and technicians involved and engineers. There's a lot of money in this kind of stuff. It's surprising to me that they get funded for stuff that no one can be quite certain how it's going to work out. But that's the scope, and I think I mentioned to you with the initial paper that was submitted to Nature with the gravitational wave project. That was signed off on by, I think, well over 2,000 authors. I mean, that's incredible. So a lot of people involved. Now, there's a question I'm going to come back to here. Are some questions beyond the collective? I mentioned it last week. Are some questions so complex and so challenging, they're simply beyond the grasp of Homo sapiens as we recognize ourselves? And I think that's true. Now, just a little brief look at this, because I've just selected a few species here. On the left side there, there's our living chimpanzees. They have brains between, say, 250 or 500 cc's in volume. And incidentally, that doesn't change much through the next, or at least for in the next 3 million years from the beginning of that common ancestor. They became increasingly skilled and spent more time on their feet, but the brain size didn't change much, and certainly little or no evidence that they were employing tools or creating tools, at least very much. And then the transition zone, the tool maker of Richard Leakey's father, Homo habilis, that's the transitional period, around 2 million years ago, maybe a little bit more or longer than that. And you notice the brain size just edging up a little bit, 500 to 800 cc's. By the way, until Neanderthals and humans, there was quite a difference between male and female size, physical size, body size, and brain size. No evidence at all that affected their cognitive talents. And there's some evidence of, as you know, just from your observation of that dimorphism, continues into our time, but not nearly as much. And then Homo erectus, this is an interesting species. It's been named, it's the longest surviving single species, but in my view, from my research on the subject, I think it's that this one definitely needs reworking, because in this case, the brain is almost doubled in size. The species has spread out throughout Eurasia and within Africa. It's taken different evolutionary lines. And so I think there are probably multiple species under this term. I don't think it's a useful term, actually, but erectus, the use of fire is associated with Homo erectus. At Heidelberg gensis, I think that's a late erectus, or middle or late erectus. But you're getting a brain that's at the low limit of human normal range. And the Neanderthals, they had brains bigger than us. Now, just for reference, there's Einstein's brain and Jonathan Swift, both pretty bright people. But look at Einstein's 1230, pretty modest. So so you can be a genius and be in the low limit of the range. So that's an interesting observation. But it does bring us to the question about what factors govern cognition, meaning cleverness, inventiveness, creativeness, imagination. That's what I mean by it anyway. And in much of the world, unfortunately, nutrition or malnutrition is a huge factor and the Gates Foundation are very involved in that. And it's no surprise that culture, wealth, and education and opportunity play a big part in how well you score. By itself, it's not very good evidence, and I can think in my own clinical neurological experience of people who developed hydrocephalus early in life, and that it stabilized, and they developed professional careers and were very capable. But CAT MRI scans, at least for some of them, just show that they had a very huge ventricles, lateral ventricles, and very thin neocortex surrounding that. So things that happen slowly in the nervous system, the brain adapts to very, very well and maintains its function. One that I think the stress on genetics, and it's a proper one, but it isn't just in the genes. We have about 25,000 protein encoding genes and a whole lot of others, and a lot of genetic material we picked up from viruses and bacteria over billions of years, which is useless. And so we carry a lot of junk with us that seemingly has no function. But the other thing about it is, obviously, before conception or just after conception, after the egg is fertilized, you have a single cell. That cell has all of your DNA, half of it from father, half of it from mother, or at least one version from father and one version from mother. And but that one cell has the potential to become hundreds of other types of cells. And it all begins to unfold within hours and over the next weeks and months and into adolescence, and in males well into their 20s. So a lot's going on in the brain and that extended development, and that's why things like nutrition and culture, wealth, and all that kind of thing, things like language seem to be innate. You don't have to teach a child how to understand and how to speak. They just do it, and that's actually quite a complex cognitive skill. And some of our social intelligence is probably genetically determined as well. But there's been a whole new world now of epigenetics, meaning you've got the same genome, exactly the same base sequence, but some genes are activated and some are silenced. Now, you know this to be true because if cells become liver cells or one or more type of liver cell, it's obviously not a nerve cell. It's not a lining cell for the intestine or a lung cell. So all of the genes that would inform those other anatomical and physiological structures are turned off. So this very active, orchestrated business it goes on all the time, but it also continues on in life with cultural influences and all of the things that I've got on the top line: culture, wealth, education, opportunity. All those play into which suites of genes are activated and which not. And so we might talk about that later. And of course, the other Nobel Prize this year is for gene editing. I've been talking about this for several years and hoping that it would finally win a Nobel Prize. It has. And by the way, I'll just show you these two books because one of them, they're written by the protagonists about there, because there's Jennifer Gouda and A Crack in Creation. And it's actually a very good book. But here's the group from Harvard and Yale, the Society of Genes. written by that group, and they both came out at about the same time. They're both worth reading. Interestingly enough, that with the award of the Nobel Prize this year, the group from MIT and Harvard welcomed the Nobel Prize for the group from California. That's a big step forward, I think, in understanding. So we'll move ahead here. So the whole question is, when did, and this thought kept coming to me through the physics series as I learned more and more about it, because it really brings up the question, when did hominins cross this threshold toward imagination, the awareness of the future, death, and perhaps an afterlife? When did they begin telling creation stories? When did that happen? Did Lucy do that 3.2 to 3.8 million years ago? Probably not. What about Homo erectus? Well, Homo erectus lived for so long, for such a long time that almost certainly within that complex dispersal, genetic dispersal to several subspecies, I think, almost certainly that's what happened. Erectus did. After all, Erectus, in its later version, is the species that later became Neanderthals, us, and the Denisovans. So yes, probably they did. The whole question is, is there any evidence that you can find of this creativity? After all, if life was lived above ground, out of caves, and there's probably not much left. So just carry on this thought. Here's the Lucy, where the name came, by the way, after the Beatles song "Lucy in the Sky with Diamonds." So, but I want you to look at the this is the successive constructions of what Lucy looked like. You notice that the top left, it's really the skull. Now look at that skull. There isn't a lot of cranium there versus the kind of around the eyes and the lower part of the face. So this is not a large brain. This is a chimpanzee-sized brain. But look at before muscles, before skin, look how it comes alive with just the eyes. Now this is something we might get into later, but much of our social intelligence and our memory of people and facial recognition algorithms for computers and artists focuses on the eyes. We read people's emotions probably more from the eyes than we do any other. We certainly don't pay attention to the ears, and probably not much for 80% of the face, unless it looks odd. But you can see he's adding in muscles. And by the way, when you see large muscles in the middle at the top row here, this large temporalis muscle right in here, I mean, mine is pretty thin. There, it's quite robust. What does that tell you? It tells you what they're eating. And it's probably grubs and underground grubs, that kind of thing, that requires chewing, and there are probably large molars at the back for that. So you get some idea of what the diet was like. So it's really quite, by the way, this is Lucy. Now, there's Lucy with hair and the proper type, probably what Lucy actually looked like on the right, but the step before that, and before the hair has been added and the coloration, that kind of thing. I love that look. It's as Gurchi says about these things, he can't work on these specimens without having a sense that he's in the presence of something living, because he's trying to imagine what they were like, what did they think, and this is Homo erectus, which Mary Leakey called dim-witted, traveler, because they inhabited, except for the New World, all of the continents. And this is Neanderthal. Actually, it's the same guy, different pictures. So, and I just want to make a point here. You know, in the last 30,000 years, we are the only survivor. If you move back, say, 50, 100, 300,000 years, well, count them up. 1, 2, 3, 4, 5, 6, 7, 8, at least 8 different species in different areas in the continent, except again for the New World. And then because of genetic evidence, we know that there were other species. We just don't have fossil evidence for them. So we know about ghost species. So there were a lot of Homo species around. Some of them with quite small brains, some of them with brains nearly our size. It just shows that at times there was a lot of variety, and many of these species had sex with one another. So they were exchanging DNA and shaping one another. So we get back to this question. It's not so much the top line. I'm not sure about that, but a harder one is, when did symbolic language emerge? When did we learn to develop? When did we develop abstract thoughts, or a symbol for something, an oral symbol for it, and much later a written symbol for it? And then if you think about art, when did narrative and pictorial art appear, and music? Well, music, we have some evidence for that, right? Because flutes, the oldest flutes, beautifully crafted ivory flutes, go back from maybe 30, 40,000 years. That's a long time. And by the way, some of them were so finely crafted that musicians this day playing those ancient flutes do pretty well with them. So, we don't know about drums. Almost certainly there was dance. And then when did evidence-based science begin? I have no idea when that happened. It certainly became a lot more common in the last few hundred years, but it probably goes back further, meaning people would try stuff out, a different way of chipping a stone and finding out, gee, if I choose my materials wisely, or find a source for a particular kind of stone that yields a better edge and it lasts longer, isn't that a form of evidence-based, if not science? Yeah, I think it is science. And then when did a sense of the spiritual develop? When did this sense of wonderment, awe? Alan Lightman really brings this. He's a physicist from MIT and Harvard, and he was the first one that I know about that actually had a joint appointment at MIT and Harvard, and half his time was spent teaching physics, and half the other time was teaching art. Now, if you read what the books he writes, you will see the two are woven together almost seamlessly. And he has this wonderful, wonderful opening chapter. He has what we would call a cottage in Maine, and he arrives at a time when it's well after dark, and all the lights are out in the cottages, and he takes this little boat out, probably 5 horsepower, has to leave the mainland to reach his island at the cottage, but there are no backlights. And he looks at it, and then he lays down in the boat, turns off the motor, lays down in the boat, looks up, and he sees what I've shown you 2 or 3 times, these marvelous pictures of the Milky Way, just absolutely stuffed with stars, unimaginably large numbers of stars, and that led him to some very interesting thinking. So I'm not going to spoil the book for him, but it's well worth reading. He's an interesting guy for sure. Well, we've talked about a lot of this. Now, one interesting thing, Steven Weinberg won the Nobel Prize, at least he shared it with 2 other prize winners for dark matter. And but he brought up this interesting question that I alluded to earlier. And he says here, we may run out of intellectual resources. We might not be smart enough to understand the fundamental laws of physics. I think there's with the issue of dark matter and dark energy, we're kind of in that. We're almost at the limits, technological limits of resolving it. There's another launch, I think the third in the row, to kind of figure out what dark matter is. They're all very expensive to try and do these things. I hope it works out, but what happens if they don't find it? So anyway, oh, by the way, he made another interesting comment. He made a number of them, but one that struck me, he said, if you want to know something, teach it. So there are certain areas that he didn't understand, so he asked the various faculties if he permission to teach that. And then he had to do all the homework for it. And that's how he learned about it. And I'm sure there was a lot more to it than that, but I like the story, and I think it's probably I think it's probably true. Now, I wanted to go back to here because this is the brain size thing, but if you look to the right is group size. Robin Dunbar, who is a colleague of mine at Oxford, he made his reputation with the claim that it wasn't tool making that drove the increase in brain size. It was social complexity, meaning trying to make sense of, if you're in a group of people, who's in, who's out, who are potential allies, who's dependable, who's not. And that's difficult because it's a moving target all the time. And any studies that have been done of our primate relatives, such as chimpanzees and bonobos, show this in spades, that the larger the group size, the harder it is to navigate. And humans are up around the 150. But you could see that the Australopiths, with those chimpanzee brains, are around 40 to 50. And that's pretty much the limit of troop size in chimpanzees, maybe a little smaller for chimps. So something to think about. Now, the other thing, this group size, this magical 150 that Robin Dunbar came up with. Well, Robin did his homework and he looked at, does that number actually hold up? Well, he came up with an interesting tabulation here. Here's a Neolithic village from 6,500 to 5,500 years ago. The average size, 150 to 200. Now you go down to the bottom, a Hutterite farming community, 107. That's, by the way, an average. And Anglican church communities, bigger than mine, 200. But there seems to be a limit on the size beyond which it doesn't work. And in certain religious communities, it's time to split up. And so we've covered that. Now, so this is the last slide, and because this is Chaudet in France, and if you look on the right, I can't see it now because I've got other stuff on top of it, but it's really to add perspective because there's somebody standing there beside the cave wall. And the one in the middle at the bottom is really quite symbolic, isn't it? I mean, it's looks like a deer or something with I mean, really quite complex horns. And that one that's on the top left, that's one that's really a very famous one. And it's one, these caves, which I think of as cathedrals, in a way, they're the longest surviving cathedrals. I mean, 30,000 years, 40,000 years, 20,000 years. That's a long, long time. And they were occupied at various times, and sometimes long gaps. The gaps are sometimes associated with rock slides that close off the cave. But going back to that top left scene, if you uniformly light the room, it is what you see. But if you take a torch that flickers, the light flickers and plays on that wall, it looks like a movie. And that cat is moving. So, and they would have been well aware of it. I mean, they didn't have 100-watt incandescent lights or steady lights. They would have had a torch, and it would have been flickering. And some of these caves and tunnels are very remote and hard to get at, and you wonder how they ever imagined that. And by the way, I'm not going to read it. I don't know where are we at in time, but one of my favorite authors, a very good writer, Richard Leakey, the son of the famous parents there. I was mentioning to Debbie here earlier that when he was a teenager, it may have been younger, his parents took him to visit several of these caves. And he was bored out of his mind. He could hardly wait to get out of them. And then, but he went back as a man in his 30s. He's now a professional anthropologist and has credentials, and he went back to some of these same caves, and wow, if you read the way he describes his experience, it's so vivid, it's so well written. It's obvious that he was very moved by the experience of being in these caves and the very shape of them and the difficulty of getting access to it. What must have been difficulty for the artist to create the stuff, so I'll just read a little part. This is Chauvet, and so standing in the Hall of Bulls, surrounded by the wild scene which exudes so much vitality and power, one is overwhelmed by the sense of another age. During my career, I've been privileged to handle many of the great relics of human prehistory, some of which I've had the good fortune to excavate myself. The sensation of connectedness that I've always experienced with them has been profound. By the way, isn't that really what John Yochi was saying in reconstructing these bodies? And has been profound. They are precious links with our past. Here in Lascaux, the emotional charge I felt challenged all that. Next to the discovery of the Tucana boy, that was probably his biggest discovery, the visit to Lascaux ranks as one of the great moments of my life. From the Hall of Bulls are two exits, each extraordinary. The first leads to the axial gallery, a narrow passageway richly decorated on all sides, a large red cow with a black head, a stag in full roar, several delightful yellow horses, and finally a large horse galloping toward the end of the gallery, where the calcite-encrusted ceiling swoops down and forms a pillar. There, winding itself around the pillar, lying on its back, its legs flailing in the air, both open as if winning, is a horse. In order to see the image, I had to contort myself into this cramped space. Imagine the challenge of painting it in the first place. Imagine the motivation to paint it there and in that position. Imagine the yellow flame of the oil lamp flickering in the cold, still air at the corner of the great cave. And then he goes on to imagine echoing down the narrow gallery the sound of rhythmically stamping feet in urgent, repetitive song. The atmosphere is tense. Everyone by now exhausted, yet taut with expectation. They know the event is near an end. Well, I'm not going to go on with this, but he ends this 2 or 3 paragraphs later, and he says, my fantasy, of course, but in these painted caves, in Lascaux especially, the images and the often inexplicable situation drive the imagination. There is a tangible power in these places that speaks of their importance in the lives of our ancestors. And that's the point we want to make, isn't it? That the imagination is given full play, and it's mysterious. And is that really any different than Maxwell and Faraday and Einstein and Planck and Bohr, who are imagining different things? The scientific method is well established, but it still requires, or Penrose, right, to bring it right up to date, and to the 1960s. Certainly none of those cave dwellers would have had a clue about black holes or much of what we know about. But don't you think it's the same imagination in play? I think it is. So I think, so one of the things that we want to do in the new year is to explore that relationship between science and art. You know, my take on and religion, if you like, because I think that the best way to look at that stuff is to take an evolutionary perspective, to realize that there was a thought singularity, if you like, to borrow a term from physics, that there was a common root ancestor for all of these human behaviors. And so they've, like the cells in our body, those behaviors have differentiated and become, they all look as if they're very different from one another. But I think at the level of the brain and how our brain actually works, to the extent that we understand it, that I think there is a common root, and I think that's what I wanted to get across with this physics series. So the physics series was really a tool to open up how humans explore mysteries and try to understand things. It seems to be a very fundamental impulse in our species, maybe less so with Neanderthals. Fairly recent, maybe goes back 200,000, 100,000 to 200,000 years, maybe a little bit longer. But it's a relatively recent acquisition. And that's what's brought us to where we are now. So I think I'm going to end on that note. And we've got time for a few questions. Oh, by the way, Peter Kemble gets the prize. I'm not sure what the prize is going to be, but Peter's come up with some interesting questions. And one of them was an interesting one about looking at artificial intelligence and the algorithms for that, and was any kind of algorithmic like equivalent for the brain. And I kind of shot back an email to him without really thinking it through, that I thought probably overrated as an idea. Well, then I went to the post office and I picked up the latest issue of Nature. And here it is: brain-inspired computing becomes complete, with the review article and then the original article. And then it's interesting reading because I think Peter's on to something, that the modeling computer algorithms on how the brain works, again, to the extent we understand it, makes sense. And so with that, I'm going to shut up. And thank you very much for attending this series. It's been a great series. I have enjoyed it, and I hope you have too. And remember that Nobel series, because now you're all prepped. You're at least familiar with some of the terms, and you can move into that and understand the physics stuff and probably some part of the gene editing. So all the best to you. Now, questions?
We can be brave and open it up to any questions if you want to ask live. There aren't, so you would just, I would ask you to unmute yourself if you have a question. If you don't have one, then just keep yourself on mute, and that way we won't have all that other noise, hopefully. But anybody have a question for Dr. Brown at this time? There's one. Mr.
Okay.
D'Souza.
Okay.
Yes.
Okay, hang on just a minute. I'm going to turn you up.
All right.
Okay, go ahead.
Okay. A couple of lectures ago, Dr. Brown, you mentioned Einstein's equation E is equal to mc squared, where m is the mass. What happens to the mass when it disappears? Doesn't it go against the law of conservation of mass in physics?
That most iconic equation was kind of a late dangling piece from special relativity, and if you look at the equation, equations are really expressions of equivalence, aren't they? One side and the other side. And this is a very profound insight on Einstein, a very courageous one, because never mind the light squared, he's really saying that energy and mass are one and the same. And if you look at quantum mechanics, at some level, they are. And certainly thinking about the origins of the universe in that first trillionth of a trillionth of a second of so-called inflationary expansion, it was very much a quantal universe, and I'll tell you, it's almost in a sense we get into trouble. I've mentioned this before with language sometimes, with words like mass and energy, and we have specific, you look up the dictionary. But in the strict sense of that equation, they are equivalent, meaning that the mass is convertible into energy, but the energy is convertible into mass. Isn't that what Penrose was really saying with the black hole? That all of that star stuff that gets sucked into or vacuumed into the black hole, it doesn't survive as stars or probably even as mass as we would recognize it, meaning rocks and atoms, even elementary particles. And what leaks out of the black hole, Hawking's radiation, well, it's radiation. And so I think the equation is clearly stating an equivalence between the two. And that's how I read it. Now, of course, it's read by most people as saying, oh, wow, look at that. Even a tiny little bit of mass destroyed or can be converted into an enormous amount of energy, meaning light squared. It's huge. That's what captures people. That's what kind of, to people like Rutherford, when they saw that, they thought, oh, wow, look what could happen. Atomic bombs, that kind of thing. Later, because that's the energy of the maybe atomic bombs, the wrong thing, but certainly fusion. That's kind of what's happening in stars, in suns. The merger of hydrogen nuclei with the destruction is probably a wrong word, but conversion of a tiny bit of that mass into energy. That's where the quanta of light come from. That's where the energy of the sun comes from. And so that's a roundabout way of describing it. But I think it's remember that other equation that I showed you, the one that talking about beauty in equations, and it was an equation for general relativity. And again, it had this equivalence, the two sides of the equation. So that's the way I like to look at it. Anyway, is that an answer or not?
I think so. It's good.
Or when you're, well, is it? Okay. Well, okay. Any other questions or thoughts, or just thoughts on the whole thing? No? Oh, you can't be that mesmerized by things. Okay. All right. Okay. Well, we'll call it a day, and I hope to see many of you with the Nobel series. I likened this to a little paper I wrote about the Nobel series. This is now the third or the fourth in a row. If this were wine, this is a really good year on the Nobel Prizes. It's a really good year. The physics prize and the chemistry prize are great prizes this year. And the one on hepatitis C is about how the healthcare system unravels mysteries, and in this case identified the hepatitis C virus. I mean, it took them 20 years actually to run down the virus. And it has a human dimension to it, because roughly 100 million people die of some form of viral hepatitis around the world, and it's devastating. It's right up there with malaria. And so that resonated with me. I was just reading some of that stuff yesterday and thinking, gee, I'm living in the middle of a pandemic with the coronavirus, but there are things that are worse, and those are a couple of them. So it's a triumph of a collective effort in medicine. I mean, there were so many people involved around the world in solving that thing. It's too bad Nobels are awarded to a maximum of 3, because there are a whole lot of people who would deserve credit there. But quite a triumph, and mostly at the NIH, National Institutes of Health in the United States, but beyond that as well. So that one, just discussing that one is the process is almost more important than the particular subject, because it shows how medical advances, a good illustration of how medical advances are made. And the same is true of the gene editing stuff. I mean, that gene editing stuff, boy, did that ever catch people napping. I mean, it's less than a decade since the first paper came out expressing, gee, if we did this and this, we could actually snip out very precisely certain genes, and theoretically even replace them with the correct gene. Wow, and it's just exploded. So I can't remember in my lifetime anything in the healthcare, basic sciences, in biology that have transformed biology and medicine as much as that, even more so than Watson and Crick back in 1953. This is really a big one. So it's one to know about. It has the ability, the possibility of really transforming the care of so many people with, even at this stage, with single gene disorders. And not only their generation, but generations to come. It's really very transformative, very politicized too. That's an unfortunate, where there's money to be made, and there's a lot of money to be made here. It gets in the way, and the Nobel Committee recognized that. So anyway, so those are my favorites, what I call the three hardcore ones: physics, chemistry, and medicine. But the Peace Prize is good this year. Literature Prize is good. I'm not a huge fan of the Economics Prize, but that's just me. So any other, I think that's it, right? Okay, all right. Well, goodbye, and we'll see you at the Nobel Series. Bye-bye.